All right, here we are, 18.1, day number 1 on parametric equations. Okay, so do parametric equations exist? Yes, everywhere, all the time. Actually, parametric equations are more applicable than your Cartesian equations. What is a Cartesian equation? It is in terms of only x and y. All right, Cartesian equations, most of the time we think of as functions. Not everything in real life is a function. Okay, so we have to have a way to represent x and y separately. So we represent them using this controlling variable t, which typically can be thought of as time. Okay, so I think of a function y equals x as two separate functions. X dependent on t, where t is the independent variable, and y, which changes based on t. Now, if you look at this graph, this obviously is not a function because it fails the vertical line test. But if you just look at the x values, what is happening to the x values? Let's say we start right here. Now let's say t equals 0 here. And let's say at this point here, t equals, I don't know, 5 seconds later. What's happening to x? X goes this way, right? So x is decreasing. And then what? Then it increases. So I don't know the exact function in terms of t, but I would say that x in terms of t is some kind of quadratic. Right? That's a function that we know of that decreases then increases. Now it might be a different strain of it. It might have some different, constant, a linear term combined with it, but that's what's happening. Now what's happening to y? Well, y increases, then what? So it increases here, then starts decreasing to here, then starts and increases again. Do we know another function that increases, then decreases, then increases? Yeah, a cubic. A cubic in nature. So I would say that y would probably have some dependency on a cubic in terms of t. Now when you combine these, you get this Cartesian equation, which can represent, whatever your parametric equations might be portraying to you. So let's look at an example, pretty basic one. Okay, here's how x and y are related to t. All right, so all I'm going to do is I'm going to fill in the table, right? And I'm going to take away my thought of like y equals x and think of x equals t. So this is like x, oops, I'm sorry. This is like x sub t. And this is like y sub t, or y of t. All right, so let's fill in our table based on those values for t. So we know t is greater than or equal to -2, which will restrict the domain of our Cartesian equation in a moment. But let's fill in some values. So if t is -2, what would x equal? -5. If t is -1, x would equal -4. If t is t is 0, I get a -3. What is this changing by each time? It's going up by 1. Oh, look at that. It's got a slope of 1 in that linear equation. Right? It's going up by 1. So I can just go ahead and fill in the rest of my values based on that. Right? That just shows a linear relationship between t and x. There's also a linear relationship between t and y. All right, my first value, if I plug in a -2, I'd get -5. It's coincidental that those are the same. That's not always true. All right, and then what does that change by each time? 2. It's got a slope of 2 in that linear relationship, so that means each time it'll go up by 2. Now what I've done is I've taken this parametric equation and I've found 7 ordered pairs for this parametric equation. There are my xy coordinates for 7 points on that. What do you suppose the shape of the Cartesian equation will be? It's going to be a line, right? Where would t equals -2 show up? Well, it'd show up at -5, -5. So right down here. And then t equals -1, t equals 0, t equals 1, t equals 2, t equals 3. And then we could go up and above and beyond as we go there. All right, now when I connect these, a parametric equation has a spot where it starts, which we know is t equals -2, and then it has a direction. So I put arrows on the parametric equation to give myself some direction. And that's the graph of that parametric equation. Now, sometimes it could come out to be a quadratic. Sometimes it might come out to be a circle or an ellipse or even something funkier than that that we'll explore in a moment. Okay. How would I write the equation of this line? What would it be? Y equals what? 2x plus what? What's the y-intercept? 5. 2x plus 5, right? You agree? But it's restricted, right? Isn't it restricted? Because it doesn't go on forever to the left. It's restricted to where x is greater than or equal to -5, right? Its domain. Its domain could be written like this. Agree with that? All right, so I'm going to show you on the next slide here how to come up with that equation. So if I want to isolate this and write this as y of x, right, or f of x, where it's in terms of x and y, I want to eliminate t. Well, what does t equal? Could I solve that for t? Sure. Could I solve for t in the other one? Sure. It'd be more complicated. So I'm going to take the easier of the two. Well, I think we can agree that t would equal x plus 3. And if y equals 2 times t minus 1, I'm going to plug x plus 3 in there. And oh my gosh, look at that. I get 2x plus 6 minus 1, which comes out to be what? 2x plus 5. So in both cases, what I did there is I only solved for t in one of them, and I plugged it into the other for t. Now here's another way for you to find that domain. We said the domain was x is greater than -5, right? Greater than or equal to. Okay, so if I say that x equals t minus 3, that tells me that t equals x plus 3. If I say that then t is greater than or equal to -2, then could I say that x plus 3 is greater than or equal to -2? Yes, because I've said they're equal, right? T equals x plus 3. Therefore, when I solve, looky there. There's the domain. Okay, take your calculator. Whoa, I'm showing you too much. Too much. Delete. And delete. And hello, Jenny. Delete that too. Delete that. I'd like you to go to mode. Make sure you're in parametric and radian. Okay, type this. 5.9 sine t in. And 8 cosine t. Now, if you think about sine is going to oscillate up and down, right? So if your x value is going to oscillate, it's going to go between 5.9 and -5.9. What's going to happen to your y value? It's going to go between what two values? 8 and -8, right? Because I've stretched it with an amplitude. So I should get an ellipse. Check this out. Oh boy. I should get an ellipse. Now, it might not look like an ellipse. I got to change my view on this because I don't think those are, no, it's going to look like a circle right now. But what I'm going to do is I'm going to go to my window. Go to my window. Oh gosh, stop. It's still working. Okay, under a window, I went a little too aggressive with my t-step. Do 0.1. Do 0.1. There we go. Okay, so it looks like a circle, but it's actually an ellipse, and here's why. I'm gonna go zoom. I'm gonna go zoom square. Yeah, I'm gonna go zoom square. There it is. Right, so it's 5.9 in the x direction both ways. It's 8 in the y direction both ways. I get an ellipse. Do you get an ellipse? Okay. Now what I want you to do next is I want you to go back in and I want to change the first one. I'm going to oscillate the first one twice as fast. Twice as fast. That means the x will oscillate twice as fast as the y will. That means it's not going to be a circle anymore. Right? Or if I oscillate it 3 times as fast. Now I don't have 2 loops, I'm going to have 3 loops. Check this out. This is awesome. You can toy with this on your own, but I'm going to oscillate the second one at twice as fast as it originally was. So there's this ratio of 3 halves. I graph that. Look at that. Now you can see it kind of, it pulsed there at both of these endpoints. I don't believe so. So this is for fun. Check this one out. This is probably one of the cooler ones. I think I went 32. You could play with these and come up with all sorts of designs. I'm changing my t-step to 0.01. Check this out. Oh my. Look at this. Isn't that awesome? Look at the symmetry going on there. It's not done. It's just going to keep rolling. Look at that. That looks like a gift just being wrapped in some kind of basket weaving skill that I have no chance in doing ever. Okay, if you would, with me, would you please go? These are pretty cool. You can go ahead and jump on there. This this right here is a really funky one with e to the t. You can go ahead and graph that on your own. And some other fun stuff. Like, look, you can make Mickey Mouse. That's pretty cool. You can toy with that. I'd like to jump into this slide right here. Look at both of these. X has a linear relationship to t, and so does y in both of them. So what do you suppose both of these will be graphed in Cartesian form? Lines. They're both going to be lines. Okay? I don't really care. Let's do one of them. Doesn't matter to me which one. Number 2? All right. So what I would do in number 2 is I would probably go away thing. There we go. Go away. I would probably make a taxi table, make a TXY table. Okay, so I'm going to do number 2, scratch number 1 for a moment. And I'm going to go from t equals 0 to 1. Oh, that's really extravagant. So I'm going to put a 0 and a 1 there. Crazy. So x has a certain relationship to t. If I plug 0 in for t, what does x equal? -1. If I plug 1 in for t, what does x equal? 3, right? So I have my 2 x values. How about for y? If I plug a 0 in for y, or for t into y, I get a 3. If I plug a 1 in, I get a -1. This is kind of funky. It's coincidental that I get, these two flipped. But all that does is provide me 2 points. So I'm going to plot those 2 points. I've got coordinate pairs now right here and right here. -1, 3, right there. That would be where t equals 0, and 3, -1, right there. So I get this, this line, and its direction would go like this. There's my Cartesian graph, right, in terms of x and y with respect to t. So could I write an equation for that line? Absolutely. Are there multiple ways? Yes, there are. Personally, on a simple one like this, I would just look for the y-intercept and the slope. So I would say then that y equals negative x plus 2. Yeah? The other way we could do it is to solve for t. It looks like a little bit more work. If I solve for t here, I get x plus 1 over 4. And then if I plugged x plus 1 in for t over here, well, that wouldn't be that bad. That would be y equals 3 minus 4 times t, which is x plus 1 over 4. So what will happen to those 4s is they'll go away. Meow, meow. And I'd get y equals 3 minus, now this is where you got to be careful, distribute that negative, x minus 1. So when I simplify, I still get negative x plus 2. So a couple different ways to get there. Right? Okay, so domain, you might just look at it and say, well, obviously it goes from negative 1 right here up to 3 right here. So yeah, sure, the domain is from negative 1 to 3, inclusive on both ends. You're absolutely right. Sometimes it won't be so clear. So what you'll want to do is take what t equals and put those same parameters on it that we have on t. So I would take that x plus 1 over 4 and put it between these two values. What should I do first to solve for x, the interval at which x exists? I'd multiply by what? Multiply by 4 on both sides. Well, that's not going to change the left. That'll be 0. In here, I'll have x plus 1. Over here, I'll have 4. Then what? Subtract 1 from both sides. Oh, look at there. And negative 1. Same domain. Yeah. So what if it's not so nicely linear? Ooh. All right. So then what? I think number 4 looks a little more intimidating than number 3. Yeah. Yeah. Okay. So let's try number 4 together. Let me drag this out of the way. Okay, so number 4. Well, the first thing I would always do is find out what t equals. T equals x plus 1. And then I would plug it into the second equation for y. I typically solve for t in terms of x because x is our normal independent variable. So I'd have 3 plus 2t minus t squared, where t we know is x plus 1. So we got a little bit of algebra to do. I'm seeing a 2x plus 2. And this is where you got to be careful. We're going to FOIL. This is not x squared plus 1. This is x squared plus 2x plus 1, right? You got to FOIL that. And then distribute that negative. So I think, if I'm not mistaken, I get negative x squared minus 2x minus 1. And I'm going to combine some like terms. I see my constants. That looks like a 4 to me. Looks like I got something that's going to cancel. Positive 2x and negative 2x, they'll go away. And then I get a negative x squared plus 4. So this parametric equation represents that quadratic right there. Okay, so I'm just going to sketch it. Now let's see how accurate I can be. Okay, so this is a quadratic that's flipped over and shifted up 4 units. Okay, so there. And then remember do you know the 1-3-5 method? With quadratics, yes or no? Okay, so you go out 1, and in this case down 1, out 1, down 1. The next one you go out 1, down 3. This is if there's no scale on the front of that quadratic term. Right, and then I go out 1 more and down 5. So if I sketch the entirety of this graph, it should look like that, right? And it'll go on forever in both directions. Of course, we're going to be restricted due to this, right? T equals 0 to t equals 3. So let's find out where t equals 0, and let's find out where t equals 3, and we can restrict the graph based on that. Because I know there's not going to be arrows on both sides if that's the case. So t equals 0. Let's find the x value for which t equals 0. So x would equal what when t equals 0? -1. Oh, right there. Bam. That's t equals 0. What would x equal if t equals 3? 2. Boom. So our graph has been restricted to a domain of what? Looks like -1 to 2. There's our domain. Now it has direction. Don't forget it's got direction. Direction on this would be from t equals 0 to t equals 3, just like that. But let's take a look at it. Okay, I want to look at number 9 real quick, because number 9's just a little bit different than what we've seen so far, although we did graph something similar. What do you suppose the shape of this will be? X is going to oscillate from 1 to what? -1. So cosine goes from 1 to -1, so does sine from 1 to -1. So my x values will oscillate between 1 and -1. My y values will oscillate from 1 to -1. I'm guessing a circle, right? So these, when you have trig functions involved, however, there is a restriction here, so I'm guessing I'll have half of a circle. When you have trig functions involved, what you want to do is you want to be careful, and you want to use identities that we know. And what I'm going to do here is I'm going to turn this into something I know. I'm going to take these both to the second power. So I'll get x squared equals cosine squared t, and I'll get y squared equals sine squared t. So what would I get if I said x squared plus y squared? What would that equal? Cosine squared, yeah, r squared. But cosine squared plus sine squared, what identity is that? That equals 1. And that right there is a circle of radius what? 1. Okay, so let me draw a circle of radius 1. Okay, here's a 1, here's a 1, here's a -1, here's a 1. I'm going to draw a little circle. Pretty good. Actually egg-shaped, whatever. Okay, so we're going to go from -pi/2 to pi/2. But how do I know where I start and I finish? Well, let's plug in a -pi/2 for a second. If I plug a -pi/2 in here, what do I get? X equals what? 0. And it's 0 in 2 places here, right? And if I plug pi/2 in here, I get 0 again, but I get 0 there. Therefore, what I've got here is I got half a circle where my parametric travels along this curve, which is a circle, from the red point to the blue point. Hari. Here. It's not always clear, but what would the domain of this be? Zero to what? To 1. All right, what values of x exist? Well, I have values. Here's a value of x is 0. This is a little bit more. The greatest value of x is right here at 1. Right? Greatest value that I could have for x would be 1. Okay, that's it for today. We'll do one more lesson tomorrow, review and quiz on Wednesday, test on Thursday, and then it's on to vectors. Like, subscribe, comment below. Eddie, I don't like the twins.